Now, after we did the equilibrium equations, we're going to develop the equations of compatibility. Compatibility has to do with the angle of twist. So, the angle of twist for each cut plus a sixth one. The sixth one is a special case because it is a statically indeterminate shaft. You treat the force, the torque at F as redundant, meaning that we need to understand what is the impact of the torque at F on the entire shaft. So first we're going to do the angle of twist of 1, which was the first cut, plus the angle of twist of 2, which is really the end of that cut, plus the angle of twist of 3, which is that cut, plus the angle of twist of 4, which, so 3 takes into account the smaller diameter, 4 takes into account the larger diameter, but you know T3 equals T4. Plus the angle of twist of 5, which takes in consideration that fifth cut, plus the sixth angle of twist, which is the impact of the reactive force F on the whole bar. So, and all of this equals 0 because they're between two fixed ends, and it will equal 0 once you get to the end. So, to jot down these angle of twists, an angle of twist equals the torque, the length of that section, times the shear modulus, divided by the shear modulus over the polar moment of inertia of that section. For 1, it's T1, 1/6 of the length. So this is 1 of GJ1. 2, T2, and this length is actually 1/3 of the total length over GJ1. For 3, the reactive torque in 3, 1/6 L over GJ1. Now, for the angle of twist at 4, we're focusing on this cross section. So, it's the angle of twist at 4 equals the torque of 4 times the length from the beginning of this cross section to where the torque, the concentrated torque is applied, which is E, so 1/6 L over the shear modulus because it's the same throughout the whole shaft, and the polar moment of inertia of shaft number 2. And 5 equals the reactive torque in 5, 1/6 L, G, and 5 is in the second bar, therefore it's the polar moment of inertia of that bar. And I wanted to erase this in order to write down what 6 is. So for 6, like I said, you have to figure out what is the impact of the reactive torque at F on the whole bar. So 6 equals the impact of F from A to D. So TF, and that's 4/6 L. So that's 2 meters instead of 0.5 over GJ1. Now, what is the impact of the reactive force F on DF? But the polar moment of inertia of the second bar will be used there. So that's the compatibility equations, and I broke it down into the torque displacement equations for the whole shaft. Now, I just want to point out that this angle of twist right here, number 2, because it's in the distributed torque, it's a special case, meaning that you'll have to integrate over a certain interval. It carries over the length of that distributed torque. So, in order to integrate, you'll integrate from 1/2 L, because that's where it ends, from 1/6 L, because that's where it starts. And you will use T2 of X dx over J G and polar moment of inertia 1. So T2 of X, I just want to remind you, T2 of X equals TA minus TX, X minus 1/6 L. So then you'll pull this into here and you'll get 1/2 L, 1/6 L, TA minus TX, X minus 1/6 L, dx, GJ1. So now you have to integrate all of this over this integral. That will break down into, once you're done, you shall get T of X. That is what your angle of twist of the second cut is equal to. Now, in order to find the reaction torques, you have to add all of these up in this equation using the angle of twist and substituting in the torque displacement equations. You substitute the equilibrium equations into the torque displacement equations. I'm just going to write it out. I'm not going to put the numbers in. I'm just going to write out what these equations should look like. Let's erase this. So, inputting the equilibrium equations into the torque displacement equations, TA 1/6 L I messed up. That was not it. You have to add the torque. So these are the substituted torque displacement equations that you're going to add up. And then don't forget the sixth one, which is for the redundancy. So you can figure out TA as a function of TF or TF as a function of TA. You can do it either way. So also, I also gave you a hint saying that 2J1 equals J2. So you substitute 2J1 into here, 2J1 into here, and 2J1 into here, and that will make everything divided by 2. And then you use all of these equations in substitute it into this compatibility equation. And I'm going to write that out. Like I said, I'm not going to put any numbers in, but from substituting everything here into it, I got the following for TF and TA. So. Well, I'm actually going to put the numbers in, but so you'll see what I got. So 0.5 TA over J1 TA minus 12. And then you add the contribution to F. And all of that should equal 0. Then once you add everything, subtract everything, you should come up with the reason why it is no more shear modulus and polar moment of inertias is because if you multiply it over here, they all cancel out. So that makes it easier. A reminder that L equals 3. So that also makes simplifying things much easier. So if you solve this for TF as a function of TA, TF equals negative TA plus 78. And this, I will substitute into the equilibrium equation, and then assume x equals 1.5 for the maximum, and we will figure out what the reaction torques are in Newton meters. So we're going to erase this. So I want to remind you all that TF equals TA, negative TA, plus 78. And remind you that the equilibrium equation was TA minus TF equals 150 x minus 345. So substituting TA minus negative TA plus 78 for TF. Doing the math, I got TA equals 75. X minus 133.5 Newton meters. So that's what I got as a function of X, that's what TA is. And then I substitute that back into the equilibrium equation for TA to find TF. And when I do that, I get, and when I do that, I will get negative 75x plus 211.5 Newton meters. So in order to find the reactive torques at the max, assume x equals 1.5 because that's what x would be at the end of the distributed torque. So TA will equal negative 21 Newton meters and TF will equal 99 Newton meters. Next, we are asked to find the internal torques of the sections. I'm going to keep up TA and TF. So for this, all we have to do is substitute everything when we made the cuts into the equilibrium equation. So cut 1, T1 equals TA, which equals negative 21. Cut 2, you have at the beginning of it, and you'll have at the end. So cut 2 at 0.5, where x equals 0.5, it will be TA minus tx x 16L, which equals negative 21 because 0.5 minus 0.5 is 0, so that would be 0. T2 at x equals 1.5, we equal TA minus 150, 1.5 minus 0.5 will equal negative 171 Newton meters. So for the third cut and the fourth cut, because they are equal, the internal torques are equal. T3 equals T4, which equals TA minus 150 times 1/3 L, where this equals 1. So this equals negative 171 Newton meters. And for the last one, the fifth torque should equal the reactive torque that we got at F. So it is TA minus 150 times 1/3 L plus 270, which actually equals 99 Newton meters. So these are your reaction torques. T1 is negative 21, T2 is negative 21, T2 at 1.5 is negative 171, T3 and T4 are negative 171, and T5 is actually 99, which actually equals the torque, the reaction torque, which means that it is correct. For the for the next one, we are going to calculate the max shear stress. The max shear stress occurs with the internal torque of T3. And I say T3 instead of T4 is because this has the smaller diameter, meaning that it will experience higher stress. So it's tau max equals the torque max 16 times pi d cubed, and it's the first shaft diameter. You can say D1 or you can say DAD. And this should equal about negative 149.33 MPa. Now, using the maximum shear stress, you can actually use this equation to find the maximum shear strain. So the shear strain max equals tau max divided by the shear modulus, which equals negative 49.33 times 10 to the 6 divided by 45 times 10 to the 9. So the shear strain equals about and it's unitless because this is pascals over pascals. And for the last one, we need to find the angle of rotation at D. In the beginning, I said we're going from the left to the right. Since we're going from the left to the right, the angle of rotation at D equals the angle of rotation at the first cut plus the angle of rotation of the second cut plus the angle of rotation of the third cut, which actually ends at D on the interval. So the angle of rotation at D equals TA 16L over GJ. That's TA minus and then over GJ1 and then plus TA minus TX times 1/3L times 1/6L over GJ1. So once you plug all the numbers in here, it should equal about 0.49 radians. I know that's pretty high because that's about 28.6 degrees. And that's huge for a shaft in torsion. But focus on the process, not actual numbers, but this is the process, and I hope that was clear to you. Thank you.